What is ISR reentrancy, and how do you fix it? Imagine you're trying to catch a bus, but every time you step onto the platform, another bus arrives and blocks your way. That's similar to what happens with reentrant interrupt service routines in microcontrollers. When an interrupt triggers an ISR or interrupt service routine, it handles quick, time-sensitive tasks like reading sensors or managing communication. But sometimes, if the system isn't designed carefully, the same ISR can be called again before it finishes. This is called reentrancy. Reentrancy happens when an interrupt can interrupt itself or when multiple interrupts share the same handler. If the ISR uses shared variables or hardware registers without protection, it can cause conflicts or data corruption. Think of it like two people trying to write on the same whiteboard at once. Things get messy fast. In embedded systems, this can lead to unpredictable behavior, especially when timing is tight and resources are limited. Why does this matter? Because in systems like microcontrollers, where every millisecond counts, a reentrant ISR can cause race conditions or data errors. For example, if an ISR updates a global counter and gets interrupted by the same or another ISR that also modifies that counter, the final value might be wrong. This can make your device behave unexpectedly or even crash. So how do you fix or avoid these issues? First, you can make your ISRs non-reentrant by design. This means disabling interrupts at the start of the ISR so it cannot be interrupted again. Keep your ISRs short and simple, and avoid using global variables inside them unless you protect access. You can also use local variables within the ISR, which are safe because they are stored on the stack. Another approach is to make your code reentrant by avoiding shared writable data. Use atomic operations or critical sections where you temporarily disable interrupts when accessing shared data outside the ISR. For example, if you need to update a shared variable, disable interrupts, update the variable, then re-enable interrupts. This prevents other ISRs from interfering during that critical moment. Prioritizing your interrupts is also helpful. Assign higher priorities to critical ISRs and lower ones to less important tasks. This way, you control which ISR can preempt another, reducing unexpected reentrancy. In some systems, you can even make certain ISRs non-preemptible, meaning they cannot be interrupted once they start. Finally, testing your system thoroughly is key. Use static analysis tools and simulate rapid or nested interrupts to see if reentrancy issues occur. For example, if your microcontroller handles communication data, make sure your buffers are protected. Using double buffering or message queues can help exchange data safely between the ISR and main program. In summary, reentrant ISRs can be safe if designed properly. Avoid shared mutable data, disable interrupts during critical sections, and keep your ISRs short. Proper prioritization and testing will help ensure your embedded system runs smoothly without unexpected glitches caused by reentrancy.